Welcome everyone. I'm going to present my work on transformer-informed trajectory optimization for relative motion in cislunar orbits. My name is Walter Manuel from Stanford Space Rendezvous Lab. So just give a brief overview before we start of what we're going to cover today. Talk about the motivation, the two key pillars, cislunar research and distributed space systems that are underpinning this work. Then I'll give some more technical background on cislunar relative motion and something our lab has been working on over the last few years, the Autonomous Rendezvous Transformer, otherwise known as ART. Then I'll present the main contribution of this work, which is the improvements that we've made to ART, resulting in a new model, ART Twin, and how we incorporate that using SCP. And then I'll present results on ART Twin compared to the original version of ART 0, and also versus a convex relaxation as a benchmark, and then wrap up with some summary and future work. So to talk about the motivation first, as we know, there's been a heavy emphasis on the return to the moon, with many countries and private companies pursuing missions in that direction, and humans to land before the end of the decade. And just as simultaneously, we've seen an explosion of distributed space systems in Earth orbit, and we can assume that this trend will continue in lunar and cislunar space, especially since, given the communication latencies and things like that, making those DSS autonomous will be even more important, especially to maintain space domain awareness in all parts of the cislunar domain, and to support RPOD operations in order to enable the nascent cislunar space economy. Getting some state of the art related to that, restricted two-body problem relative motion models are less useful in the lunar environment, so things such as the HCW, Yamanaka-Anderson, Willis-Level-D'Amico equations and state transition matrices can't really be used, and these are what a lot of current DSS research is based on. So we'll need to use models more tailored to the restricted three-body problems, such as those derived by Franzini, both the linear and nonlinear equations of motion, and as well as other models that leverage the manifold dynamics, such as local toroidal coordinates. And it's a more challenging dynamical environment to deal with due to the nonlinearities and chaotic nature, especially at rapid passages like periloon. So when we're setting up these RPOD scenarios, they'll include non-convex constraints such as passive safety, etc. And these optimal control problems are typically computationally expensive and solved offline, which conflicts with the focus on autonomy and onboard computation that we mentioned in the first slide. So another piece of the state-of-the-art is transformers, which, as I mentioned, our lab has developed the Autonomous Rendezvous Transformer, or ART. Transformers, as we've seen in the rise of LLMs, they're neural networks that predict sequences, but these don't just have to be sequences of words. They can be sequences of trajectory, sequences that form trajectories, including the states and the control inputs. And the ART can actually serve as a warm start for SCP in order to have SCP converge faster for the purposes of trajectory optimization and solving those non-convex OCPs. ART's also been shown by our lab in previous work to have used as a tool for rapid mission design. However, in all previous work so far, it's been limited to Earth orbit on spacecraft relative motion. It's been limited to Earth orbit scenarios that only use linear dynamics. So this leads to our open research questions. For which tools or methods can be used, first of all, to efficiently, effectively, and reliably solve non-convex OCPs? And then if we consider using tools such as ART, what improvements do we have to make to transformer-based methods in order for them to be capable in this domain? And will they not only be capable, but actually provide an advantage? So the contributions this paper proposes are we create a new version of art using forward-backward shooting called Art Twin. And we apply this new model to cislunar R-pod scenarios, and we find that in individual and batch testing, Art Twin demonstrates significant gains in runtime and efficiency. So going briefly through some technical background, a lot of this is probably familiar to the audience, so I'll go quick. We'll be working, the key reference frames we'll be considering in this work are the synodic rotating frame that's moon-centered and the LVLH local frame centered around the chief and anchored at the moon. And the equations of motion we'll be using are the CR3P relative dynamics models proposed by Franzini that are derived in that LVLH frame. And we use both the nonlinear and the linear versions when applicable. Then getting into art itself, there's three phases of three major components associated with using and developing this model: dataset generation, model training, and model inference. So with dataset generation, we basically generate a diverse set of boundary conditions. We set the distributions for them, and then generate a data set of about 100,000 of them. And these are solved trajectories, warm started by convex relaxation of the problem and solved via SCP. And then the model, the transform model itself, is trained via least squares loss minimization on all of those sampled 100,000, well, on a training split set of those 100,000 trajectories. Then once we have our fully trained art model, then we can use it to auto-regressively infer and predict the next steps in a trajectory. We're using the dynamics in the loop version of art. So you can see the art will propagate one step, come up with the control input for one step, then propagate the dynamics forward, and then to the next step, and then loop back around. And so this initial guess, which may not be perfectly accurate, but it still helps SCP converge to a better local minimum and find an optimal solution faster and more effectively. Now getting into the specific contributions of this work, where we've developed Art Twin, which incorporates forward-backward shooting. And the difference here is that forward-backward shooting generates two arcs, one from the initial state and one from the desired terminal state, and then patches them at the midpoint. And the hypothesis behind taking this approach is that it will help speed up convergence and especially minimize terminal state error, which could prevent SCP from converging. And so the only change in the data generation and training pipeline is that in the training process for Art Twin, we'll randomly assign each token, each sample, each trajectory sample that it's trained on, a token DT or negative DT for the time step. And then that particular step of training will either train Art Twin to propagate forwards or propagate backwards. And now with our trained Art Twin model, when we move on to the inference step, we generate both a forward arc and a backward arc. And as you can see, it generates an initial guess that's patched at the midpoint. And then that's again fed into SCP and converges to an optimal solution. Ideally, better than the original version of Art 0 would. And then it's still a work in progress, but these are the optimal control problems that we're solving considering this particular work. Problem one is a convex linear relaxation that is used for the as the convex benchmark, the basically alternative to the ART warm start. And then for the actual optimal control problem that requires SCP to solve, we have a nonlinear dynamics and a non-convex approach ellipsoid and keep out zone constraint, which requires the use of SCP where we employ the SCVX algorithm, SCVX star algorithm, and the passive safety constraint is linearized at each iteration. And we still use nonlinear dynamics via Taylor series expansion so that the final converged solution is identical to nonlinear ground truth propagation. And so for the simulation and experimental results, we generated a diverse data set with large distributions in initial state but a fixed terminal state near the target's chief spacecraft so simulating kind of like a rendezvous scenario. And importantly, this rendezvous scenario is starting at Paraloon. So we're really trying to show how ART and an ART twin can be effective at the areas where the dynamics are most chaotic and nonlinear. So you can see in the left-hand plot, of the chief orbit, the R-pod segment is starting near Paraloon. And this is the sampling of a subset of the actual full data set that was generated of solved SCP trajectories that with the approach ellipsoid pictured. Yes, I know. And then first we compare ART twin to ART zero. Again, this is the original version of ART that just propagates forward only. And so we can see on the right-hand side first, just as one example, you can see how the ART zero in the blue propagating forward doesn't quite reach the terminal state. Whereas ART twin in red generates one arc from the initial state and one arc from the terminal state, and then still gets, so of course it satisfies those endpoints, but has a discontinuity in the middle that requires patching. And we can see on the left-hand side that there's a good amount of error in both the midpoint breakpoint gap of our twin, but even in some cases a large amount of error in the terminal deviation for ART zero, the terminal state error. And what this leads to is that in a lot of cases, ART zero is unable to converge at all. It reaches 20 iterations, which is the max, and doesn't really find an optimal or feasible solution, whereas ART twin is able to converge usually in about 3 steps, 3 iterations of SCP, which drastically decreases the runtime. So this establishes the necessity for forward-backward shooting, why we made that enhancement. So just some quick notation for the upcoming plots. SCP-CVX is the solved SCP trajectory warm started by that convex relaxation, and SCP-ART is the solved SCP trajectory warm started by ART twin. So this is just one example test case where we can see that the CVX and ART twin solutions both converge ultimately to similar SCP solutions with similar delta V costs, but their initial predictions are very different, and ART twin is much closer than the final converged SCP solution, which of course would help speed up its runtime and speed of convergence. And so we can see that highlighted in this right-hand plot, where SCP-ART takes half, or actually fewer than half, as many iterations as SCP-CVX, to converge and has a speed up of 4.1 seconds, so almost 40%, and more than 40%. And also notably, the initial guess by our twin maintains passive safety throughout, as opposed to the convex guess, which doesn't take in the non-convex constraint into account. And so then when we do a batch evaluation over the entire test data set of 10,000 samples, we see that the cost in terms of fuel optimality is not too different between the converged solutions. But again, the real strength comes from runtime and efficiency, where our twin provides a speed up of more than 1.5 times on median. And so this really provides example of how this can be of how our twin provides a boost for onboard computation and in-space autonomy for computing these kinds of things online when you can't necessarily afford to wait that extra for your solution to take 3 times or 2 times as much. So to wrap up, we've shown how transformer-based warm-started methods, specifically ART, can be made more viable by incorporating forward-backward shooting. We showed how by upgrading ART0 to ART-Twin and applying it to the cislunar domain for the first time, that resulted in advantages in efficiency and optimality. And this will all help to enable autonomous distributed space systems for RPOD and space domain awareness applications in cislunar space. And future work will include training and testing on a more diverse and general set of rendezvous scenarios and higher fidelity modeling and potentially alternative state representations, since ROEs have helped, relative orbital elements were very useful for setting constraints in the original ART0 formula in Earth orbit. So that wraps up the presentation. I'll take any questions.